Welcome back. This lesson we're going to be looking at domain and range. Now, before we start that, we want to talk about what an ordered pair is. So an ordered pair is just a list of x and y values that belong together. So, for example, 1, 2 is an ordered pair. So the y value 2 goes with the x value 1. It also looks like a coordinate. When we talk about a relation is a set of ordered pairs. So it could be, for example, x, y, such that you've got 1, 2, for example, 3, 4, 5, 6. So when you're sketching these out, then you just have a set of little dots. So 1, 2, 3, 4, 5, 6. So they're separate ones. Whereas we could do a linear equation and then would have a connected line, whereas in a set of ordered pairs, just discrete separate dots. So, keeping that language in mind, a set of ordered pairs, if you just think of the values as the x value and the y value that belongs with it, or as a coordinate, you'll be fine. Now, when we're looking at the domain and range, the domain is talking about all the possible x values for a relation, possible x values. So for that first one, if it was 1, 2, 3, then the domain would be the discrete points x equals 1, x equals 2, x equals 3. Or we can often give a domain as an interval, so you say all the values between 1 and 3. A range is all the possible y values. Now we'll have a look at some examples in a sec, but you might be given a domain and asked to sketch it, or you might just be given a relation with no domain, and in which case we're looking at the implied maximal domain, which means all of the possible x values that would realistically work in that equation or relation. So let's have a look at a couple examples, and hopefully it'll make it a little bit clearer what I mean. So the first one up here, we've got state the domain and range for each of the relations represented by the following graphs. So we can look at question A here. We can see you've got a straight line linear equation, and it's going between the points -2, -1, up to 2, 2. So we could write the domain, which is our x values. We can see that the smallest possible x value is -2. And we can see that we'll just make it a little bit thinner, -2, and we see it's a coloured in circle, so we have a square bracket, and it goes up to +2, so it'd also be a square bracket. Another way we could write that is x belongs to -2 to 2, or -2 is less than or equal to x, which is less than or equal to 2. All three of those are writing the same thing, so whichever one you feel comfortable with. Okay? Then for the range, we're doing the same, but this time we're doing it for the y values. So the smallest y value is at -1, which would be here, and it goes up to +2 as well. So we write -1 to 2, or y belongs to -1 to 2, or -1 less than or equal to y less than or equal to 2. Okay? I'm just going to tidy up. So again, they're just ways of writing the same thing. So let's leave it just as the top two for now. And we'll use this notation more frequently throughout this chapter. So let's look at the second one. We can see we've got a circle now. So for this one, the domain, we look to the smallest possible x value. You can see here it crosses the x-axis at -2. So that'd be -2, and the graph is a solid line, so it does exist at -2, so we have a square bracket, and then it goes to +2. And likewise, the y values go from -2 to 2 as well. So the range would also be -2 to 2. Okay? Looking at this graph up here, let's say we were asked to sketch this one. And you notice that we've got y equals 3x plus 2, but then at the end, we've got this little bit here, which reads as, and this is familiarizing yourself with these new symbols. We've got x belongs to negative infinity to positive 3. So it's saying, can you sketch this straight line, y equals 3x plus 2, but only for the x values up until positive 3. So, just like we would normally sketch a linear equation, we can look, we've got our y-intercept is at 2. So there's our y-intercept at 2, and we need one other point, so we could use a gradient of 3. I always like to do the two intercepts, so when y equals 0, I'd get negative 2 on 3, or negative 2/3. And the graph would go all the way through here, going to infinity and infinity. So that's what a normal graph looks like. But now we're looking at, hey, we want to restrict that to just from negative infinity up to positive 3. So where is the graph at x equals 3? Sub that in. Y would equal 3 times x, which is 3, plus 2. So we get 9 plus 2 is 11. So therefore, the endpoint is at 3, 11. So at all the way up here. And it's a curved bracket, so we have a hollow circle. So at 3, 11, and then the graph exists all the way down, and we just do a little arrow to show it's going down to infinity. Okay, so if we had to state the range for that, we'd say the range, the highest possible y value is 11, and he said going down to infinity, so negative infinity up to 11. Okay, and the domain was given to you in the question, which was negative infinity to 3. Okay, so that's a common thing. They give you the domain up here. One last example of a question you might come across is where they don't give you the domain. So you can see here, I've got sketch the graph stating the maximal domain and the range. So here we've been given an equation and there's no domain written at the end. And these are similar to the graphs you would have sketched in the past when first learning about it. So the type of graph this is, you can see there's x in the denominator to the power of 1, so it's a hyperbola, and it's the power of a positive x in that equation, so it's not, there's no reflection there, and we've got translations of plus 3 up, and would have 5 on 2 in the x direction. So let's put our asymptotes in first. Let's do all the heavy lifting. There's our axes. Would have at positive 3. So that's at y equals 3 would be one asymptote, and then the other one would be at x equals, if we make the denominator 2x minus 5, we go, hey, what value of x can we sub in to make all that 0? So that would become 5 on 2. So at 2.5 or 5 on 2, however you want to do it, just leave it in the fraction form there. 5 on 2 is our x asymptote. So hyperbola, positive, so we're going to be up here, and we're going to be somewhere down here. Where does it cross? Let's find our intercepts. Okay, so I could have 2 there, or I could go through the origin, or I could have 2 here. So I don't sketch that part just yet. I want to find my intercepts first. So sub in x is 0. We'll give us our y-intercept, so y equals 2 on 0, which is 0, so I get plus 3. Well, that's not going to work, is it? So that's not 0, it's 2 on minus 5 when x equals 0, plus 3, so we'd get negative 2/5 plus 3, which I can write 3 as 15. Oh no, sorry, 3, yes, as 15 on 5. So I end up going positive 13 on 5 is where my y-intercept's going to be. So that's going to be at 2 point, there we are. Let's just call it 13 on 5 there. You can write it as decimals if you want, but I like to leave it in fractions. And we're going to have another one down here on our x. So when y equals 0, I end up making all of that equal to 0. So then I have minus 3, and I can rearrange that. It gets a bit messy. Let's do that down here. So 2 on 2x minus 5 plus 3 equal to 0. Move the minus 3 over, and then I have to times both sides by 2x minus 5, and then I'm going to divide it by minus 3. So I'm just going to swap the denominator. I'm going to swap all of that with that. So I get 2 on minus 3 equals 2x minus 5. So then I'm going to get 2 negative 2/3 plus 5 divided by the 2 equals x. So tidying that up. What will we get there? 15 on 3. So that'll become 15 on 3, which I can write as, what's that going to be? Positive 13 on 3, 13 on 6. Nice question to pick out as an example here. So 13 on 6, and there's my hyperbola going like that. So that's what the hyperbola looks like. Now, the maximal domain, alright, implied by this is that x, as you notice here, it's going all the way to negative infinity, and over here I should have arrows going up to positive infinity. The only point it doesn't exist at is the asymptote. So we could say either negative infinity, now there's a long way of writing, negative infinity up to 5 on 2, double inclusive, or 5 on 2 up to positive infinity, or you could write it as all of these set of reals, so every possible number except the value 5 on 2. So the set, that's my set brackets, which are terribly drawn there. There we go. So that means that it's all the possible numbers from negative infinity to infinity except for 5 on 2. And from this, therefore, the range would be from negative infinity going all the way down and all the way up, except for y equals 3. So we'd say it's all the real numbers except for 3. Okay? Hopefully that makes some sense. When we're not given a domain, we just say what's the possible maximal domain that you can have. So for this hyperbola, it's not at the asymptote, and then we find the range from it. If we had a linear graph and we're given a domain, then we can use those endpoints to state the domain and range. Alright, good luck with the questions, and we'll do some more worked examples in our next video.